IBM. And unlike you guys, I'm not a database architect or a Linux guy or a Redis geek that they made me put this sticker on. I'm a hardware systems engineer for IBM in Houston. I spend my time building engines to support the things that you guys are playing with. And what I've got here is I have one of my customers slash students slash colleague at Louisiana State University. We were going to do a Google Hangout where Argo was going to be on the screen for you, but it got too complicated, so we're going back to simple telephone, microphone, Argo, follow the slide. And I spend my life going around the area that I work in to listen to business problems and apply those business problems for IBM to put in analytics compute engines. And in this particular case, everybody in here, I believe, knows something about Linux and something about databases, right? Okay, you're all computer scientists, right? Nobody in here is a life scientist. Raise your hand if you're a life scientist. All right. Can you spell DNA? You can't spell DNA. Okay, this is about DNA and computer science coming together. Okay? And so Louisiana State University is one of my customers. Argo is a PhD student in his final year at LSU. And he and I worked on a project last year, which is a very complicated, very hard science to do with compute. And we utilized IBM systems and the Redis database to do some revolutionary things. And this little talk it's going to be about 30 minutes to 45, but it's about the use case of what we did, how it applies to Redis, the outcome that was great, and that may not apply to anything you do in your world today, but it's about a really high-speed database crunching billions of four-letter files in 7 hours. Okay, that's the end result. So genome analysis is one of the hardest life sciences computational techniques to perform. It is the area in which it has significant impact on your and my life going forward, the lives of our kids. And the challenges are, how can we do it faster, better, cheaper now? And that's what we're trying to get to. And Redis became a tool of that. Dr. J. Park is the lead scientist at the Computational Center at LSU. This was his project. Argo was the researcher. I was the engineer that put the systems together. Next slide. So what we're going to talk about is a little bit of just very simply about the genome assembly problem. I'm going to try and put it in computer context, and if I miss it, Argo's going to correct me. And about, who knows about Hadoop? Everybody knows Hadoop. Who knows about graph in Hadoop? Graph reconstruction. This is about Hadoop and graph with Java and Redis. Okay? And accelerating that process with an IBM server and an FPGA. Who knows what an FPGA is? There you go, Field Programmable Gate Array Accelerator. And how IBM has harnessed an FPGA with external storage for a giant computer memory brain that's available to you. Okay, next slide. So Argo, here's the picture of all these slices. So I'm trying to put this in low terms. Argo's better at it than I. But the fundamental problem is when they take your DNA, they get a sample, they run it through a machine, and it produces millions and millions of four-letter amino acid names in a giant long sequence, and the challenge of the world is to put that back together in your unique sequence. And so it's all these purple, yellow, red, and green, which represent the four amino acids, all jumbled together, and how do we put it in a unique sequence that identifies you? And that in itself is basically what I call a great big giant sort and assembly of commonality. And it takes lots and lots of compute cycles. And as an example, this analysis produced upwards of 1 billion four-letter files on the file system all at once, or over the course of this analysis. So you have genomes. They are sheared into variable parts. They're unordered. we have to put them back into an order. And so the computational science is down here at the bottom, putting them together in the correct order in which they are in your body, or in the body of, in this case, it was what's called a metagenome, which is all the genes, all the genomes in the gut of a cow, which was everything all mixed up, which is even harder. Okay? That's the simple life science part. Next slide. Okay, so what's happening is, who knows what Moore's law is? Okay, I'll say it anyway. Moore's law says that no matter how big I give you a computer, you're going to fill it up and use every bit of it, right? Basically, the more I give you, the more you're going to take. And so at some point, the computer can't do anymore, and you got to have more efficient code or other things happen. So it's the same as happening with genome assembly. The problem is that it used to take hundreds of millions of dollars to do a genome assembly in the early days of life science. Today, scientists are trying to get it down to $10, $20, $100 so that you can give a sample or whatever the sample is for, and it can be done for a very small amount of money. It's a very computationally intensive problem. And we have to harness our IBM systems to do that, and we are way better than our competitor, who everybody in the room knows, called Intel. Okay? And I'm going to show you why in a little bit. Okay. So it takes huge storage space, extreme I/O performance I've been talking about, and lots of compute cycles. Okay, next slide. So this is kind of a characterization of this genome reassembly and how the MapReduce in Hadoop takes the common letter codes, and if you think about 5 characters, what are these for? And then what are the next 4 from the second one? And you march down the whole string in groups of 4, and then put them back together in the proper fashion. That's what the graph does, i.e. all the blues, all the yellows, all the greens. That's the big problem. Okay, so what we embarked on was the fact that this is what's called high-performance computing, actually. And high-performance computing is a total parallelization of compute cycles. And basically, in layman's terms, you take a math algorithm and a data, and you put it on this computer, and you take a math algorithm and data, and you put it on this computer. So you take chunks of all the data, and you run them in total parallel fashion across a whole lot of compute nodes, and then they are reassembled back into the answer. That's high-performance computing. And next slide. Yes?
They have an excellent HPC conference at Stanford University.
Great, great. There's a supercompute conference every year. This year it'll be in Salt Lake City in November. It's a very big topic. It's the smartest people I've ever met in the world in the room. You might be one of those, right? And I work in Houston, actually, and so I work in a totally different space, which is called oil and gas. And I actually had a joke the other day with all these seismic guys, and I said, what's the difference what's common between seismic processing and DNA? And the answer was, well, seismic under the earth, 3-dimension, is really the DNA of the earth, and here's the DNA of your body. So I gave this example. Anyway, it lasted a little bit. So here's the problem that we encountered. At LSU, they have and had a 120-node Dell high-performance computing cluster. So this is 120 Linux nodes all together operating in parallel fashion. And this particular analysis that I'm going to talk about took over 25 to 30 hours to compute and get an answer. Okay, so how does that compare to IBM? Well, IBM has a unique characteristic that Intel does not, and you can take advantage of it in your world, and Redis takes advantage of it. And that's called symmetrical multithreading, simultaneous multithreading. If you don't remember anything else today, remember the number 8. Is that simple enough? The number 8.
Yes.
IBM Power Systems have the ability to process 8 threads per core. So on a compute processor, we have 2 processors on the server. Each processor has 10 cores. So that's 20 cores times 8. That's 160 virtual cores all running simultaneously. The maximum you can ever do on any Intel system is 2 threads per core. Okay, so this particular exercise was to prove that this would actually have benefit. And I'm going to walk you through what happened. Okay, so what we did is we took the same method that they run on their 120 node Dell cluster, and we moved it literally Argo on the phone remotely in Baton Rouge, copied the Java code and the Hadoop and the data set. We had to actually go to an old-fashioned method and FedEx a NAS array with a 3 terabyte file on it up to New York, and then we had to bring it back into the computer because the laws of physics were working against us on data file transfer. So, thank you, FedEx. Anyway, Argo and his partner got on the computer, and on Monday, Tuesday, and Wednesday of whatever particular week, this was June of last year, they brought that same methodology, that Hadoop code, the algorithms, the Java, and they brought it onto our system remotely, and we did some testing and tuning, and ultimately by Wednesday afternoon we had the system ready and tuned out, ready to go. So we were working remotely on all together in emails like everybody does, and we said go. And so on Thursday morning they fired up the big run. I'm going to talk to you about the details of it in a minute, but the net result was that what took 30 hours on the Dell cluster of 120 nodes took 6 hours on the IBM system with only 40 nodes. So that's 3 times faster with 1/3 less nodes equals 9 times performance. That's what you can take advantage of in your particular whatever you're doing, whether it's science or database construct, but it was the real proof. And so this picture actually is just a little schematic of compute nodes and storage architecture. That system produced, Argo, how many temporary files did the first stage, so the Hadoop in Poughkeepsie, how many temporary files did it produce in that 6-hour period?
Temporary files, or you mean the graph files, the permanent?
Well, a little bit of both.
Okay, if you consider about the temporary files, there were almost 5,000, sorry, not 5,000, it was almost 10,000 mappers. So for each mapper, they produces 2 temporary files possibly. So it was 20,000, and finally it was like, how many reducers did I use?
A big number.
So, yeah, that was a big number actually. So it was no less than 5,000.
Okay, so bottom line was it produced a whole lot of scratch files while it was doing the computations, and it was all able to keep up, and we did it 9 times faster than Intel could even do. So, next slide. Okay, so I'm not going to talk too much about, this is what I just talked about, 120 nodes, 40 nodes. This is, it was an Infiniband network. If you know anything about networking, that's the highest networking protocol in high-performance computing. Next. We had to run a little test cases in order to make sure we didn't blow up or run the thing out of gas. We ran some test cases. First one was a 12 gigabyte data set, then a 70 gigabyte data set. But, I'm sorry, 12, then 90. And then we went to the big guy. And the big guy was the actual test, which is a 3.2 terabyte data set of DNA data. And it produced, at the end of that 6 hours, it produced an 8 terabyte metagenome set. I call that stage 2. This is where Redis comes in. So they could not do that before in a reasonable amount of time. So that was part 1 of the proof project. And that 8.6 terabytes then went to the next step, the next stage, which was the graph reduce of that data set. Okay, next slide. If you're interested in Hadoop parameters Argo, I think you had about 160 VCores running per server, correct?
Right.
Times 40 servers. So whatever that comes out to, 6,400, something like that, yeah.
Is SuperMike 2 the Dell one? Or is
SuperMike 2 is their name of their Dell cluster, right? Yeah, the IBM was in our customer center in New York, okay? And all this was remote. Okay, next slide. And two things we were trying to test and prove, and this is directly applicable to Redis also. One was scalability of Hadoop VCores or threads with over time. So near linear scalability by increasing the number of VCores and putting everything running in parallel. Okay? On the Intel line, it would have stopped right here. So, next. That talks about, this actual presentation was made at the Open Power Summit. Let me stop there and talk about that real quick. IBM did something this past 2 years that's different from what they did before. IBM took our power processor and we put it into the open source community. It is part of what's called the Open Power Foundation. You as companies, you as developers, industry, software providers, you can be members of the Open Power Foundation and you can contribute your unique thing to Open Power to the community, and you can take advantage of this threading or this performance as your unique adaptation or value or contribution. So when you see the word Open Power, that means that it's the power processor and somebody in the open community is doing something with it, whether using it or adding a value to it. As an example, Google and Rackspace in the last month have announced that on the backside of what you see, there will be Rackspace Open Power servers and there will be Google Open Power servers that they are going to make with our chip and take advantage of all this performance, which threads is one thing, I/O is another, and cache is another. And when you put all three of those together, that's what makes the secret sauce. Okay, next. Skip that. I don't want to. This presentation was made at the Open Power Summit in April here in San Jose for all the people involved in that space. It's a conference for Open Power. So the highlight here is that the end result of that first test was a 9x performance improvement over anything they could do before. So as a result of that, LSU became an Open Power Foundation member, and now they are contributing Open Power intellectual property contribution to the community. And this is one of those, and more work that Argo and his colleagues are doing are forthcoming. Next. Okay, let me talk a little bit more about how this works. Now I'm going to the Redis part. Okay, IBM has something called the IBM Data Engine for NoSQL. Redis NoSQL database. IBM Data Engine is putting harnessing all our power of network, storage, and servers together for that purpose. Whether it's a rack of them or one server. Yes?
you didn't address this during the first part of the presentation. You made mention of an FPGA.
Yes.
Specialized FPGA that you used during this processing. Was that any part of the presentation so far?
Hold that thought. Coming up next. All right. The FPGA, his question was, where is the FPGA in this? You're a great straight man. So stage 2, that 8.6 terabyte data set reassembly required. So who has a computer, a server with more than 2 terabytes of memory in it? Nobody. You can't do it. Right? We do. Through an FPGA, I'm going to talk about it. Next. Okay. So what happens is IBM has created or invented a process with an FPGA called the Capi interface, Coherent Accelerator Processor Interface. And what that means is that the FPGA and whatever's behind it can be seen through this interface as processor memory. Okay, so that means that IBM, have a 10, 20, 50 terabyte array on the back connected to this FPGA, and now my processor brain sees 10, 20, 50 terabytes of memory. That's what we put to use here. It was 10. Now that's also costly, but that cost is coming down, and later this year we're introducing an FPGA with 2 terabytes on the board. Okay, next slide, next slide. How this works, back up. How this works is that, I don't have a pointer, that the power server over there and the flash array are connected through the FPGA interface, and the memory, this memory on the disk, is seen by the server as processor memory. And in the case of Redis, Redis is the go-between in this case to put the Redis database on this large memory array and treat it like memory in the processor, memory to the processor, and that's what we did. That's what this stage 2 analysis was about. And in that, in a 2U server, that must be 24 times 8 is 192. Is that where that comes from? I think so. 192 threads in a 2U server. That has to be our 12 core times plus 12 cores times 8 threads, I think. Okay, and on the back, we could put up to 56 terabytes of memory behind that. So, this is really useful for science. As the cost of external memory comes down and the capability goes up, it becomes now more relevant to you in whatever you're doing in a commercial space. Okay, next. How this works is Redis has an API, and that API does the read-write block level I/O access to our array, and you are able to put your key value stores in the Redis database out on this large memory, and they're treated as, they're executed at processor speed. Next. A little bit more about that. I think this is the same slide in a different twist, but it's called the Capi attached flash system. And this illustrates the alternative being lots of compute nodes versus one or more servers versus servers and flash arrays. Next. I'm going real fast here. In fact, this is not going to take 45 minutes unless you ask a lot of questions. But one of the trade-offs, one of the things you have to figure out is your application latency bound or processor IOPS bound? Either way, you can choose your realm of operation, right? Before now, you were bound by how big you can make the memory, right? Now, we can make it pretty much unlimited. Then it becomes a question of economic feasibility. Can you afford it? Is it the right purposeful engine? Where does it fit in your thing, whatever that is, whether it's a real-time Twitter feed analysis or processing live streaming video or something. I don't know what all the use cases are represented in the room, but the technology is there today to do this. We're actually using this technology not with Redis, to do video image processing real time of live action surveillance cameras to pick out particular faces out of a crowd with this same kind of technology. So, you get to choose your path of pain, if you will, and that corresponding economic value of that. Next. So now I'm back to the Genome Assembly issue, and we're almost done. The Genome Assembly was taking all these 4-letter words, organizing them into their relative pairs, and putting them back together. Well, that's this 8.6 terabyte memory problem that we stuffed into the processor brain, and the answer came out. Next. This is actually the last slide. This is the big one. So, in one server, what could not be done before was one server took a small part of that 8 terabytes and processed it in 7.5 hours. They could not do it before. So, and this is actually a little snapshot of the throughput that was coming off of the, this is the Redis graph. I'm pointing to the graph in the upper right, Argo, which is 154,000 writes per second on the system. The bottom graph is 1.13 gigabytes per second throughput through that engine. So I don't know how that equates to your particular database applications. Maybe it's phenomenal, maybe it's not enough, I have no idea. But it's the realm of possibility. And bottom line was that this particular science project produced a result that couldn't be done before with technology we have today based on large memory application through an FPGA with Capi, Coherent Accelerator Processor Interface, and Redis was the engine behind it. I think that's the last slide. Okay, our guy is a PhD student at LSU. There were 2 other guys working on it. I'm just a systems architect. And go back one. We did this last fall. We're moving on to some other ancillary things now, but it was relevant to what's capable in the world today. We have customers who they're not in my purview, but we have lots of customers running Redis and this technology for things like real-time Twitter analysis, real-time access to financial transactions. I'm starting a project in about 2 weeks in Austin with a financial trading company. We're starting out proving the server just like we did before, and that's going to then evolve into this same FPGA interface for high-speed financial transaction applications for stock trading. And it is so... It used to be that IBM systems cost about 4 times more than any Intel box. Therefore, there's 10 million Intels and not so many IBMs. But today, we are almost at parity. So now I'm going around and proving that the economic viability of this technology is there, and you can get more out of your, you can harness more compute technology today for your application. Any questions? Yes?
So in this case, is the Redis a giant key value store?
Yes.
How many keys?
I don't know. Let me ask. That's where I needed him. So Argo, the question from the floor is was the Redis database a giant key value store? And of all those key values, how many key values did you have to load and did it process in the Redis database in that test?
It was in terms of several billions of key values, so I cannot remember the exact number, but yes, it was in terms of billions. And
Was that
sorry?
Was that million or billion?
Billion.
B, with a B.
With a B.
Yeah.
B.
Yeah, it was billions of key value stores in 7 hours, right? That's the magnitude. Does that answer your question? Yes. Yeah, okay. Anything else? Yes?
What would you say is the system dollar comparison between Supermike and Power 8 system that was used for this?
So the first phase, Supermike, so some rough math, was over 100 nodes, and every node is roughly $10 to $20,000, so we'll round up and say 15 million and a half. 40 nodes at maybe 20, so half the cost, okay? And 9 times more performance, thus the economics, right? Right, and his boss, Dr. Park, immediately shifted from Intel to IBM for future research, right? And Open Power Foundation, by the way, you can go there, openpowerfoundation.org, I think. You can join for, universities join for free. I don't know about vendors, but you can begin to tap into that and produce your own contributory value. You can contact IBM. They get guys like me. We come out and find out how does our system apply to what you're doing, and then we'll put together the right formula of a system, see what makes sense, and we can even test it out. We got a center in New Jersey ready for your stuff. Okay, one thing I left out, and I'll ask Argo the question here in a second, that particular second stage application was multiple shards processing simultaneously. How many shards were in the Redis when we did the test with Redis? I think it was like 6 shards.
64.
How many?
64.
Oh, okay. So another point to my multiple threading, that was 64 parallel shards of Redis running simultaneously for the billion key value stores, right? But I didn't answer your question, though. There was another part of it.
Which cluster
It was not a cluster.
is individual instances?
Well, this was one server with 64 shards. I don't think they were clustered together, right?
Can you explain InfiniBand?
Infiniband? Sure. Really fast network, 56 and 100 gigabit per second. Is that right? I think so. Faster than Ethernet today, and primarily only used in high-performance computing, but it's costly, right? So inside the compute complex is intercomputer and interprocess network on InfiniBand. Outside the computer is normal Ethernet 10 gig or 40 gig. Or Fiber Channel's disk. Fiber Channel is the protocol of disk communication. This InfiniBand is the network protocol. FCOE, Fiber Channel over Ethernet, is fiber channel packets embedded in Ethernet packets. Make sense? Yeah. So in general, it's inter-server connectivity, what I call it inside the rack or in the racks, but the cost structure of InfiniBand pervasively, it's come way down, but it's not pervasive in normal Ethernet. And the InfiniBand guys would shoot me for not being able to explain that. Well, the FPGA is the accelerator, and the special interface on the very first slide we had has special code that IBM created to make the accelerator be coherent with the processor, but it was the only way to do that.
Is this a prototype?
No, this is commercially available right now today. I can sell you one. You can, in fact, there's a company right here in California named Edico, E-D-I-C-O, who uses our power server, an FPGA, to do a single server genome analysis.
Why would you do that instead of baking it into the silicon?
That's a different question. I'm not a silicon engineer to know why it can't get down to that level. Yeah, good question. Man, you quickly jumped over my head. I'm not the engineer at that level. I can tell you that when you use the accelerator, something like 2,000 instructions are utilized. When you're on PCI interface communication, it's 20,000 instructions. And so you get a 10-fold increase, right? But there's some really smart system hardware engineers in Austin that can answer those kind of questions. That's above my pay grade. All right. So I don't know if that was useful, but I hope it planted a seed that the realm of possibility exists, that Redis, high-speed, IBM Power, remember the number 8, and call IBM for help. That's where I'll leave it with you. And you'll never know if it works unless you call us, right? All right, thank you very much.